Welcome all, and thank you for joining today's webinar brought to you by Wine Australia and the AWRI. My name is Robin Dixon and I'm a Senior Viticulturist at the AWRI. I'm joining you today from Jacobs Creek Visitors Centre, where we're hosting an autonomous tractor demonstration. So we've got about 150 people out there watching tractors drive around with no drivers. So it's been a great morning. If you're interested in finding out any more information about this project, jump onto the AWRI website and search autonomous vehicles. Simon Nordesgaard is the engineer in charge of that project. So yeah, it's a really great project. I encourage you to jump on and learn more about it. In the spirit of reconciliation, the AWRI acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. I would also like to acknowledge Wine Australia for providing funding and support for webinars via the AWRI Extension project. In this session, we'll look at irrigation scheduling tools to make every drop count. It's always good to have a webinar like this when we've got lots of rain around. But before we jump in, to make a start, a quick few reminders about asking questions. So you can ask questions at any time using the Q&A section of the Zoom. So it's the Q&A button down the bottom of the Zoom toolbar. Type in your questions at any time. We'll be doing the Q&A section at the end of the webinar. And this webinar, as with all our webinars, are recorded, and a link to the recording will be sent out to you after the webinar. So for anyone who's joining, welcome. Today's webinar topic is irrigation scheduling tools to make every drop count. And it's a great pleasure to welcome Dr. Everard Edwards, Dr. Vinay Pagay and Jeremy Giddings today. So first up, we're going to hear from Everard Edwards. Dr. Everard Edwards started his career in the UK with a Bachelor of Science with honours in plant sciences, followed by a PhD in post-harvest physiology of potatoes. He then undertook postdoctoral fellowships in the UK and Australia, both examining the effects of climate change on plants. Since 2006, Everard has been applying his background in whole plant physiology to perennial horticulture at CSIRO. Much of this has been in optimising wine grape management, including climate change, vine balance, and various aspects of irrigation. More recently, he's been leading a broad research team at the CSIRO that is combining technological and viticultural know-how to develop new digital tools for vineyard management. Everard, if you're ready to make a start, I'll hand over to you.
Thanks for that. So I've been asked to sort of give an introduction to this session around how vines use water, what drives their water use, the basics of, I guess, thinking about irrigation, and an introduction to plant-based sensing, which Vinay in particular will talk about a bit further on. So as not being a commercial grower, I always think it's useful for me to remind myself, as to why we're actually irrigating the vines. And, primarily it's so that we get an economically viable crop. So in terms of, what happens if we don't, it's because we're growing vines in areas where they'll be under water stress, which, may impact the productivity and affect the fruit composition and thus its value. And so when we think about how much we need to irrigate, really it's, how much we need to produce the desired yield and quality of fruit. And secondarily, I guess, at some point we have to replace the soil moisture used by those vines, otherwise we're driving down soil moisture indefinitely until it's too dry. So looking at the vineyard, we can consider the different components of water use within that vineyard, and we would expect the largest one typically to be the actual transpiration of the vines itself, of course, but we also have water use from a cover crop if that's in place. And if the cover crop's not in place, or if there's a mix only in place for part of the season, we've also got evaporation occurring from the soil or the soil between the plants and so on. And finally, we also have deep drainage. So this is where the water has moved through the soil and it's got out of the root system and off down towards the water table. So the deep drainage, I guess, in terms of irrigation is really an interaction between the way the water is applied and the composition of the soil. And so it's not something we're really going to address here today. So those remaining components, we can lump them together and term that the crop evapotranspiration, which is a term I'm sure you've all heard. So coming then to look at the vine transpiration, and this is also true of any cover crop that's in place, when we consider what's actually driving the water use of the vine itself, obviously one of the largest factors is the evaporative demand of the atmosphere. So we can consider the vapor pressure deficit of the air around the leaf. So to demonstrate that, what I've got on this graph here is actual water use determined through sap flow sensors of individual vines, litres per day. And as a surrogate for the evaporative demand of the air, I've simply plotted this against reference evapotranspiration. So the numbers are not necessarily supposed to match up, but it does give us that measure. So what you can see on this data here, and for those of you who've seen it before, I apologize because I've been using this data set to demonstrate for a while. But just how strong the relationship, and this is across a whole number of vines in there, just how strong the relationship is between evaporative demand of the air and the water use of the vine. So obviously at different times of the season, when it's cooler weather, early and late in the season, we're at the bottom end of that line, and in the middle of the season, when it's particularly hot, we're at the top end of that line. And it's worth noting that this data, which is all taken when the canopy is close to full grown or full grown, just based on the difference in the atmospheric conditions, we've got a threefold difference in water use for the same vine there. So obviously the next factor is the actual size of the canopy. So clearly the bigger the canopy, the more water it's going to use, because you've got more leaf area for that water to evaporate off from. But interestingly, as the canopy gets larger, we've got more self-shading, we've got more influence on the boundary layer around the canopy, so higher humidity against the leaf. And so like if you compare the blue and the green dots on this figure here, the blue canopies are actually quite a lot larger than the ones on the green, but because they're actually got to be really quite a large canopy here, we don't get a sort of linear relationship between canopy size and the water use. On the other hand, where we've got a smaller canopy, that's obviously reduced the water use quite a lot. So then the final major driver of the water use of the vines itself is how open the stomatal pores on the leaf are. So you probably remember that the underside of the leaf itself is covered obviously in a waxy cuticle, and the underside of the leaf we've got these small pores, which is where the water evaporates out from, and the opening of those pores can actually be regulated by the vine. So these bright red dots there are actually exact same vines of the dark red dots, but when they have closed or partially closed stomata. So this is actually generated by water stress, but doesn't really matter. However you close the stomata, you get the same effect. And so you can see that by closing the stomata, those exact same vines under the same atmospheric conditions have used significantly less water. So when we consider the crop evapotranspiration as a whole, and we consider how we can efficiently irrigate, the simplest, sort of conceptually simplest way of irrigating is simply to replace the water that has been used by the vineyard. So to replace that crop evapotranspiration. So then, of course, the question is, how do we measure the crop evapotranspiration? You can actually do that directly using a system called an eddy flux tower. Obviously, having one of those in every vineyard is quite impractical. It's also be seriously expensive, but we don't really have to go that far. We can also estimate the evapotranspiration of the crop using mathematical modelling based typically on meteorological observations. So, you know, there's commercial vendors who will assist you in doing this and use the, you know, some of their own modeling. But typically these models are based on reference evapotranspiration equations that were sort of established and standardized in the 1990s. And these basically take a reference crop, which is actually 12 centimetre sward of grass, and they can accurately model that purely from weather station observations. So then what we need to do is to scale our actual vineyard water use against that reference crop, and we do that using a scaling factor crop coefficient. Now, most commonly, this is kind of a bit of a guesstimate, and so it's where we really lose accuracy with that. So I think, but Jeremy will be discussing methods of looking at crop factors and irrigating to ETC in his talk a little bit later on. So a second way of thinking about doing maintaining full irrigation, rather than actually having to estimate the crop evapotranspiration, because all of that water is basically, you know, coming from the soil, is to actually look at the soil moisture and maintain that soil moisture, you know, throughout the season. And obviously this is what, in one way or another, quite a lot of growers are doing. So we need to monitor the soil moisture to do that. Now, you know, you can go in with a spade, as in the old days, but that's not giving you a great estimate of the whole rooting system of the vine, particularly with drip irrigation where the water is not applied to the whole vineyard surface. So normally we're using soil moisture sensors to estimate how much water is in the soil, and there's two types of these. One of them will measure soil tension, the old gypsum block type of system. Now this is great in that it represents the actual way the plant sees the water in the soil. The downside is you can't take your soil tension measurement and, you know, simply estimate a number of millimeters to refill that soil back to where it was on a previous day. So this is more easily done with a capacitance sensor, which does give us an estimate of the volumetric soil water content. So we can simply calculate how many millimeters we need of irrigation we need to add to maintain the soil moisture. So where this system becomes a bit more difficult is because these soil moisture sensors are expensive. So most properties have only got one in, you know, every 2, 3, 4 blocks, whereas we all know that the within block heterogeneity of the soil is quite high. So depending on how well placed that sensor is, it can make a real difference to how well we can maintain full irrigation using soil water content. With either of these methods, we also have questions around the frequency of irrigation. So the less frequently we irrigate, the less well we're replacing that evapotranspiration or maintaining soil moisture, and the vines might be under stress for part of it. On the other hand, if you do pulse irrigation, you know, every day or multiple times a day, you'll get far less variation in the soil moisture, but often it's not the most water efficient way of applying. It may suit some soil types, not others. You know, and generally most growers are actually wanting to generate some degree of stress for part of the season with their vines. And so when we want some degree of stress on the vines, it then becomes quite difficult to use either of these two measures, because it's hard to link a proportion of evapotranspiration or a certain reduction in soil water content with a specific water stress level of the vine. So ideally what we want to do is to combine these kind of irrigation strategies with plant-based sensing, and again ideally at scale, so we can look across the vineyard. So what we really thinking about is we want to know the water status of the vine. And when we talk about that, I guess really what we're meaning is how much water stress the vine is under, to what degree it's got enough water to maintain photosynthesis and so on, and what degree it hasn't. So the vine obviously has an absolute requirement for water, and it uses water in various processes in the plant as well as maintaining the tissues. But the reality is that 95–98% of the water that's going into the root system is leaving the plant into the air. It's simply moving through it. So that water basically is we consider it as part of a continuum from the soil to the roots, through the plant to the air, and it moves along a pressure gradient, a negative pressure gradient, and we can measure the negative pressure at each part in this system, and that's what we term the water potential. So it could be soil water potential, stem water potential, leaf water potential, or even water potential of the air. So it's measured in megapascals. And so if you think about the air itself, so this is typically sucking a lot of moisture out of the surface, and we might be at -100 megapascals. And then when we look at the soil, you may only be at 0.03 megapascals, 30 kilopascals. And so that is a huge gradient from the soil to the air. But the water is only moving where there is a gradient. So the roots have to be more negative than the soil. The stem is going to be more negative than the roots, and the leaves are going to be more negative than the stem. And again, that's this is where the water is all leaving the plant. So if you remember back, I mentioned the stomatal conductance and how the plants can change the stomatal opening depending on the situation. And so the end result of that is that whenever we look at water potential, it's actually a dynamic process. So if we look at leaf water potential of a well-irrigated vine, in this case, we've got around about -0.3 megapascals, and this is pre-dawn, so this is before the sun's come up, and it's in equilibrium with the soil. It's not the same as the soil, but it's in equilibrium with the soil. Once the sun comes up and the light hits the plant starts photosynthesizing. It opens up those stomata, the water is evaporating into the air, and so the water potential of the leaf then drops down. It becomes more negative, and that's because the plant cannot replace the water as quickly as it's being lost from the leaf with the stomata open. So all of the restrictions through that system, it simply can't get water into the leaf as quick as it's leaving. So the water potential drops, and then at some point during the day, the plant is recognizing this is, getting to a semi-critical point where, there's risk of damage to the leaf. And so it closes the stomata up, and that stops the water potential dropping any further on. And that will depend on the atmospheric conditions and the region as to where that point exactly is. If we now consider a water-stressed plant, and so again, it's in equilibrium with the soil at night, it might be in this case -0.7 megapascals. When we get through the day, those stomata, because it's stressed and it's getting stress signals, they never open up fully. And so we can actually get a situation where, when you come in at midday, the leaf water potential of the stressed one is less negative than the well-watered one. Now, this is only going to happen under very high evaporative demand conditions, but it can happen, and it means that simply looking at leaf water potential doesn't always well match the actual water stress the vine is experiencing. So this dynamic is important. So how do we look at the water potential of the plant? And with plant-based sensing, so many of you will know the pressure chamber or pressure bomb, and some of you may use that. So the nice thing about this is it's a direct measure of the water status of the plant, because we're balancing that leaf negative water potential. We can also make an estimate of the stem water potential, which is a bit more reliable than that leaf one under these sort of very strong evaporative demand conditions that I just mentioned. And we do that by bagging the leaf so that it can't transpire, waiting till it becomes in equilibrium with the stem, and then measuring it in the same way. The downside is this is very destructive, and it's very manual process and quite time consuming. So typically not ideal unless you've only got small areas that you're looking at. Other ways of directly measuring stem water potential are using psychrometers, or more recently a microtentiometer that's available. Again, these are direct measurements. They're in the stem, and they have the advantage that they're fixed in there, so they're relatively long term and they're continuous. So in terms of those dynamics I was talking about, we can look at that if we need to, and understand, the reality of whether that vine is under stress or not. Related to these measurements, we can also use dendrometers. This is an indirect measure. So what happens is during the day when the water potential decreases, basically the stem shrinks microscopically, and then at night when it refills again and comes into equilibrium with the soil, it expands out again. So with a dendrometer, you can measure that daily up and down of stem diameter. And we can then look at that in conjunction with weather data and determine whether the diurnal change is as big as we would expect, given the weather data that's occurred. And so when those two things separate out, we know we've got vine stress. So this is an indirect measure, and we now do require environmental data to really understand it. So another system you can use, which really also is best used with weather information, even though it's measuring actual water use, is the sat flow sensors. Grapevines have very heterogeneous flow within the stem, so it's difficult to get them in exactly the right place and get a super accurate measure. You need quite a few of them. But even with a very small number, you can track, like with the dendrometers, you can track the diurnal increase in sat flow and then the drop off at night. And we can see it over the season and so on. But with weather data, same as dendrometers, we can sort of estimate whether we think there's as much water flowing as we would expect, and if not, irrigate accordingly. So I was also asked to briefly mention spectroscopy. So this is something that's sort of quite different. Basically, when we shine light onto a leaf, leaf's green, so you've got an interaction between that light and the structure, the chemical makeup of the leaf. When we do it with near infrared light, it has these very strong absorption by water in particular. So on that solar spectrum down the bottom end, there's a number of big dips. There's one at just below 1,000. There's another one at just over 1,100. Another one about 1,400 nanometers. They're all caused by absorption of the sunlight by water in the air. And it's the same on the leaf. So we can shine light onto the leaf, look at the reflectance spectrum and make an estimate of the water content of that leaf, and thereby understand what the water potential is. The problem is that very small changes in water content drive quite large changes in water potential. So you've got to have a really good calibration, and your calibration is affected by other things such as the leaf structure, and that's affected by the environment it's in and different varieties and so on. So it's definitely, it's proof of concept. It's been there for quite a long time, but in terms of getting a good calibration across a broad area is probably very difficult. Also, the instrument itself is actually quite expensive. So the last thing I just want to briefly mention in terms of plant-based sensing is thermography, and this obviously has had quite a lot of interest and press over the years. So here's an infrared image of a vine, and we can see how much cooler the vine is than the ground underneath it. You can also see an irrigation patch of cool ground in the adjacent row, and you can see that the berries there underneath are warmer typically than the leaves. Now, this is a really nice image. That was a $45,000 infrared camera, and it's only at one point in time. But we can see those differences, and they're differences that I've often had growers talk about, that they feel the leaves on a warm day and the stressed ones will be warmer, and obviously this is a real thing, and so we can actually use that to make an estimate of the stress the vine is under. And that's, of course, because the transpiration from the vine is providing evaporative cooling. and that's the water coming out of those stomata. If we block the stomata, you can see just how much evaporative cooling is going on. In this case, we block them all up with Vaseline. We can see how much the leaf temperature has risen. So that's the kind of difference that it makes. And then, we can demonstrate the effect of the transpiration on leaf temperature by spraying that leaf with cold water. So this is the whole, with water. So this is the whole surface now, and get that evaporative cooling. So you can get quite big differences, although usually they're small. So basically, the greater the water deficit, the more closed the stomata are up, the less the evaporative cooling, so the higher the leaf temperature relative to the atmosphere. Now, and that's the key thing, is we do need to look at this relative to other environmental measures as well. But the other interesting thing about it is that because we've got stomatal conductance that's driving this temperature response, we can actually mathematically make an estimate of stomatal conductance, which is a little bit different from water potential, and potentially integrates more stresses and so on the vine. So it gives us possibly a bit more information. So if we don't have a $45,000 camera and a lot of time to do it, there's again commercial companies starting to offer methods of doing this, the different sensors or different systems. And here at CSIRO, we've been developing one which is called the proximal, which actually does data fusion using an RGB camera and a much cheaper low resolution thermal camera to be able to sort of dynamically estimate leaf temperature, canopy temperature, even with the changes in the canopy size with growth and so on. And so Vinay, amongst with some other plant-based sensing, will go into that shortly. So just to summarize, when we think even of the very simplest optimization of irrigation, replacing only the water use, it can actually be quite complicated to implement and require quite a lot of information. On the other hand, we can do full irrigation without direct measurements other than knowing weather, climate conditions, and some information about your vineyard. But I do think that if you want to have accurate and repeatable application of deficit irrigation that's reliable from year on year, it's really quite difficult to do that either without a lot of experience, which you may have, but other managers may not, or without using sensor data. So in the past, this plant-based sensing has been quite difficult to implement. It's been expensive. It still is both of those things to some extent, but I think increasingly we're seeing a market appear where some of these devices are becoming both more practical and more affordable. So just to bear in mind though that really getting exactly what you want out of your vines still requires some knowledge of what the plant's doing with these sensors. And the other thing, of course, is that plant-based sensing can't predict the future. So if a big weather change is coming, your plant doesn't, and so you still have to manipulate the irrigation strategy you're using to take account of that. And that finishes me, other than to thank, I guess, the various staff that have taken data I've just looked at, and Wine Australia that funded most of our work.
Thank you, Everard. Now I'd like to introduce Dr. Vinay Pagay. Vinay is a senior lecturer in viticulture at the University of Adelaide. His basic and applied research lies at the intersection of grapevine ecophysiology and vineyard technology. His current applied research is looking at the use of proximal and remote sensing tools to obtain high spatial and temporal resolution data of both biotic and abiotic stresses in vineyards, as well as for precision irrigation scheduling in vineyards. Over to you, Vinay.
Thanks very much, Robin. Can everyone hear me okay? Hopefully my voice is coming through. So thanks very much for this invitation, and it's great to be sharing with you some of the tools that we have as vineyard managers and irrigators, and Ev has given a very nice overview of plant-based sensing, as well as some of the physiology that underpins some of the sensing that is available to us today to make irrigation decisions. So this is going to be somewhat of a continuation of Ev's presentation around what options we have in terms of optimization of irrigation in vineyards. And when I refer to optimization, what I'm really talking about is matching irrigation applications with what the crop really needs. And so Ev has mentioned things like, characterizing soil moisture, using sap flow sensors, etc. All of that is actually quantitation of crop water needs dynamically over a period of a day or several days or weeks. The time span, during which an irrigation decision or decisions have to be made. So it's really trying to match application with need. And vine water demand, as you would know and has been mentioned before, is results from a number of different factors, including obviously site and environment, but also management practices can have a pretty large effect on how much water the vines actually use. Particularly as we manipulate, for example, leaf area through shoot thinning, for example, even changing our crop levels can impact on transpiration rates of the vine. And obviously, genetics play a role, and we know that very well here in Australia. We take advantage of differences in genetics to, for example, plant cultivars that are more water use efficient or tolerate more heat stress, etc. So all of that actually plays a role into impacting how much water you would need to apply as an irrigator. Now, this is something that Ed has already presented on, so I won't spend a lot of time, but there are a number of methodologies that can be used. The eddy covariance method, which Ed mentioned, is a flux tower-based measurement. It's a very expensive setup that actually looks at fluxes of water vapor coming off a surface, and that surface could be a vineyard or any other surface. But there are some commercial versions of flux towers now that are based on a technology called surface renewal, making very accurate temperature measurements along a vertical gradient. And so there are companies now that have commercialized that for estimation of things like crop evapotranspiration. So that's basically the amount of water that's removed from your vineyard, and that's the amount you may want to replace or a fraction of that amount that you would replace. Other instruments are perhaps more research oriented, such as some of these leaf gas exchange instruments that give you not just transpiration rates of single leaves, which is their big limitation, but also things like photosynthesis. So you can actually see what the benefit of having a certain water status is on vine productivity and carbon assimilation. Really a useful tool, but perhaps more in the realm of researchers. Now, sap flow sensors is something Ed touched on. This is something that's commercially available. A number of companies, both here in Australia as well as in the US, sell sap flow sensors. And these can be really useful to quantify canopy water use, albeit with some caveats around, using, for example, environmental weather data to make adjustments or calibrations to the sap flow, and also being aware that the grapevine is highly heterogeneous in its vascular structure in the stem. So that makes it challenging to get repeatable readings depending on sap flow placement. And I'll talk a little bit about sap flow sensors and what sorts of calibrations are required. And obviously then an extension of gas exchange is a whole canopy gas exchange system, which I'll talk about, where entire vines are enclosed in chambers. So some of the options that you would have as an irrigator are in the domains of either soil moisture sensing or plant sensing, as Ed has touched on. And plant sensing obviously traditionally has been around use of pressure chambers, but increasingly growers are having access to more continuous based approaches, such as sap flow sensors, dendrometers, which is shown here on the bottom left of that red light, the red line. And there are some continuous versions of thermography towers and things like that coming online as well. Growers obviously here in Australia have got familiarity with soil moisture sensors, whether those are gypsum blocks or whether they're capacitance probes. Neutron probes aren't really in use anymore for various health hazards, etc. But really the gypsum blocks and the capacitance probes are really what's being used quite extensively. And Ev touched on this, differences between soil tension with the gypsum blocks and soil volumetric water content with the capacitance probes. Now, the capacitance probes are really nice because you get the multi-depth measurement, and some offerings of these C probes can also give you things like temperature of the soil or things like EC estimates, so things like volumetric ion content and things. So if you're in a situation where the salinity is an issue, you may consider a C probe, a multi-depth C probe that gives you estimates of apparent electrical conductivity. So that's quite nice. But again, we're starting to get more and more interest, as I've said, on these plant-based sensors for various reasons that relate really to the uncertainty of where the roots are relative to the soil moisture sensors. And there are a number of examples where we and others have seen the plant water status being quite different from the soil moisture and inconsistent with that. So clearly the roots are not always where the soil moisture sensor is, and that's where I think we're starting to see a shift towards the plant-based sensing. This is something I think that really motivates a lot of what I think irrigators are faced with in terms of a challenge and the motivation for us to do research in terms of space. Characterizing within block spatial patterns of water status. So in this case, I've got an example on the top right where we've got different depths to impermeable layer, in this case limestone. The lighter colors in the block are shallower regions under about 30 centimeters in rooting depth. The darker regions are upwards of a meter in rooting depth. And you can see very clearly in the thermal image, this is obtained by a fixed wing aircraft with a thermal camera. The one on the left is an NDVI, which is a multispectral image. You can see patterns of spatial temperature, of canopy temperature that relate very strongly to the rooting depth. So in terms of rooting depth, this is something that, again, can't be captured by a soil moisture sensor. The plant responds very, very clearly to rooting depth. So again, motivating the use for plant sensors here. The other motivation for this is the placement of any sensor, whether that's a soil moisture sensor or whether that's a plant sensor. Getting a spatial map of variability across a block will allow you to then place sensors strategically in perhaps the weaker zones or the more stressed zones and perhaps the wettest zones. And then that allows you to start zoning your irrigation system, so valving, and then starting to optimize, essentially not putting a single irrigation level on across your block, but putting on a split irrigation level based on variations that have been predetermined through remote sensing, as we've shown here in this image. So I'll go through in the next 10, 12 minutes, I'll present a few case studies where I show you different options for you as growers to characterize and quantify your water requirements of grapevines in terms of providing guidance to schedule irrigation, both when and how much to irrigate. The first one is out of a study we did in Riverland using a gas exchange technique. So this is measuring the transpiration rate of the vine over the course of the day. So this is under fairly hot and dry conditions in the Riverland here in South Australia. And we looked at differences between Shiraz and Chardonnay vines that were fairly large, fairly productive, having yields upwards of 25 tons a hectare. In some years, they would be upwards of 35 tons. But this was data from last year. And you can see the leaf area is actually being quite large. So these are massive canopies, very productive with crop factors that are in the range of 0.75 to 0.8. For those of you that do ET-based scheduling, and Jeremy will talk about ET-based scheduling, a crop factor, an accurate crop factor is really critical to get their numbers right in terms of irrigation. So we measure crop factors for every vine using a light interception approach. Happy to talk about that if you're interested offline. And so what we found is that based on an irrigation application of about 22 to 26 liters per vine per day, this is on fairly warm days, the canopy transpiration rates as measured by the balloon is upwards of 30 liters per vine per day. So these are really large vines and transpiring at their full potential with really good soil moisture. And we're talking about the pre-dawn values of soil moisture being more than -3 bars. So really no stress on the vines in terms of water stress, plenty of water. The vines are going to use as much water as they can get. So in this case, we get transpiration rates upwards of 30 liters a day for Shiraz and Chardonnay. And when we compare that with a crop evapotranspiration method, again, this is using reference ETO numbers from BOM or using energy balance, as Ev was mentioning, together with a crop factor, that KC value I have on top of the irrigation line, we get numbers that are very similar, all right? So about 33 to 34 liters per vine per day. So pretty staggering amounts of water that these vines are using. When we calculate water use efficiency, we're interested in optimization and actually making every drop count. We're getting water use efficiencies in these vineyards of upwards of 4 tons per megaliter, which is actually quite a bit higher than the average across Australia, which is closer to 2 or 2.5 tons per megaliter. So these vineyards actually do really well with good canopy management and good crop levels. We're getting a really good water use efficiency out of these vineyards. Like I said, we'll also try out these sap flow sensors that Everard introduced. And we also mentioned that these sap flow sensors require a degree of calibration, and also they have to be assessed in terms of the environmental conditions. So the box I've highlighted here for you for Chardonnay and Shiraz show two bars. The one on the left is the uncorrected value. So they essentially plug and play, comes out of the box, put it into the vine, and you get values of about 10 to 12 liters per vine per day around harvest, just an example. So these are sort of uncalibrated sap flow sensors. But when we calibrate these sap flow sensors against these whole canopy chambers, you can see the numbers actually starting to line up a bit closer with those chambers as well as with ETC. So this is just a point to make that these sap flow sensors can't be used straight out of the box. They require a degree of calibration and interpretation as well. So best to work with somebody who's actually had some experience with them before just using the numbers as they are, because they do underestimate actual transpiration rates quite significantly if they're not calibrated. Now, the value of these sap flow sensors, to us, this was really revealing. It was, using them during heat waves. So how much extra water does a vine need when there's a heat wave? So we did this characterization last year in Chardonnay and Shiraz. Again, you've got ambient temperatures upwards of 35 degrees, almost touching 40 degrees on a warm day. And that occurs, over 3 to 4 days at a time. So what we find is that the canopy transpiration rates go up by about 13 to 14% compared to the pre-heat wave period. And what's interesting is that even after the heat wave, you see the transpiration rates actually not maintained, but actually drop quite significantly compared to the pre-heat wave. So that's a suggestion that perhaps the vines had experienced a little bit of stress, and those stomata that Ev was talking about that are pores or valves for water transport out of the leaf, those have perhaps closed, or there's been a depletion of soil moisture. All right, so that's perhaps led to a closing stomata and a decrease in the post-harvest post-heat wave water use by about 12 to 14%. So in terms of mils, I think you are probably more familiar with mils per day. You look at the additional transpiration during heat waves between 1 and 1.4 mils per day. And the additional irrigation that was applied was about 1.7 mils per day. So in fact, even here, by just doing the simple sort of water balance, if you will, between the vine and the soil, you can see that there's an opportunity here to save water by between 0.7 mils and 0.3 mils per day. All right, so that extra irrigation of 0.7 to 0.3 mils could have been saved had we known what the sap flow values were. So this is actually another way to optimize. It's actually to look at temporal relationships of irrigation application and vine responses, even during heat wave conditions, which we tend to see a lot of here in South Australia. So good to know what the vines are using in terms of water under the hottest conditions as well. And this is where these plant-based continuous sensors are really valuable. Now, another type of sensor, as Ev has mentioned, is something called a microtensiometer. You would be familiar as a grower, especially if you've been around for a few decades. Soil tensiometers have been extensively used in agriculture, perhaps less so in viticulture. But essentially, the soil tensiometer gives you a measurement of soil water potential. So that's been miniaturized and available commercially through Florapulse, showing you here in the device, in the picture in the middle. So you get these lovely continuous measurements of water potential, which is sort of the level of stress in the vine. And here I have some arrows. The sort of brownish arrow gives you the highest value of water potential from these continuous water potential sensors. And that's really an estimate of soil moisture, as I've mentioned. And the lowest value shown in the orange arrow is the minimum water potential of the vine, which gives you the maximum stress of that vine. Okay, so that you can get an idea of soil moisture availability to the vine, the roots as they see them, and also the maximum stress the vine is enduring over the course of a day. And you can see effects here, as I pointed out in arrows, of things like the soil moisture response in the blue arrows in response to irrigation. You can see responses to changes in vapor pressure deficit, which is a composite term incorporating temperature of the air as well as humidity. And so the plant is actually our best sensor here. It's responding to what it has around it, whether that's different moisture levels in the soil or different demands from the atmosphere, which are reflected in the VPD. All right, and this is what the stomata are responding to drive transpiration rates and determine how much water that vine is using. So the plant is actually our best sensor, and these types of sensors actually give us a really good idea of what's happening both in the soil as well as in the atmosphere. So we're just interrogating really the plant to get an idea of the stress level that it has and what it's experiencing relative to its location. and also its entire root zone. All right, so we're not worried about where that soil moisture sensor is. What does the plant have access to in terms of moisture? Now, the interesting thing here is we compared Cabernet and Shiraz with these tensiometers, and I'm just making a point here that relates somewhat to what Ev was mentioning with the stomatal closure under the deficit irrigation situation, and where water potential can start to be misleading and go wrong a little bit. So here you can see in this yellow box, we have in the middle graph a depletion of soil volumetric water content. That's the percent soil moisture you get from a C probe, dropping from 35 to 25%. But curiously, the lowest value of your the red line on the bottom graph starts to rise. That's suggesting that the water potential is climbing and the plant is less stressed, which we know is not correct because the soil moisture is depleting. The VPD is constant, so the plant should be getting under more and more stress. So what's happening here is Cabernet is having a slightly different response to Shiraz. The stomata are perhaps more sensitive to changes in soil moisture and are closing, and therefore the water potential is underestimating this true stress of the vine. So this is where understanding of the physiology, as I've mentioned, is really critical. Cultivar specific differences in responses to soil moisture availability and vapor pressure deficit are really important, and knowing what types of metrics are relevant for irrigation are really important. So the last thing I'll present on the proximal plant-based sensing is around these thermography towers. Again, Ev has mentioned a proxy crop that CSIRO has developed. We've got, Adelaide Uni have got our own version of this similar type of thing without the RGB sensor, so ours is not as fancy, but commercialized through a company called Athena. And basically there we looked at Shiraz and Cabernet, where we conventionally irrigated some vines versus a sensor-driven approach. The sensor-driven approach was driven based on specific understanding of the responses of stomata for Shiraz and Cabernet to irrigation and specific thresholds we had developed to increase water use efficiency. As you can see here that from the data sets that we didn't change berry size or quality parameters, anthocyanins and berry tannins, but you can see that our irrigation levels dropped off considerably in the sense treatments where we drove irrigation based on canopy temperature as a proxy of transpiration. And we greatly increased crop water use efficiency, the tons per megaliter, driving it based on a plant sensor. So the conventional, I should add, was also driven by a soil moisture sensing partially. So there was a sensor-based approach there, but it was based on soil moisture sensing. So this is from A-grade blocks. So imagine the potential in lower grade blocks. All right, so this is the value of plant-based sensing. This is the reason why growers are getting interested in this technology as opposed to soil moisture sensors and others. Now, finally, just in the last few minutes, I know I'm running out of time. I'll just talk about remote sensing because a lot of people, industry have been approached by companies providing remote sensing services, whether that's from a satellite or whether that's from a fixed wing aircraft or that's from a drone. So you've got a number of different platforms that you have access to these days through a commercial provider, and some larger companies may even have their own in-house remote sensing teams with drones, etc. So you've got a number of different platforms and you've got a number of different sensor options depending on the types of questions and data you're asking. You typically have multispectral type cameras installed where you're looking for, vegetation indices like NDVI to characterize things like, canopy health, biomass, things like that. You might use a thermal sensor, for example, to quantify canopy temperature and then convert that to measures of stress using various types of reference temperatures, etc. So you have lots of different options. And again, it's good to understand the limitations and the advantages of each of these options. So just again, a few case studies of how remote sensing can be used if you're considering remote sensing for your business. In this case, we did a study on a regional basis using a fixed wing aircraft and mapped the entire region of Coonawarra over several years. And from this thermal imaging of vineyards across Coonawarra, there were about 12 blocks. We extracted some very basic canopy temperature indices of stress. On the PCA plot you see here on the right side, the top right quadrant, TC minus TA, the canopy temperature minus the air temperature, having a very strong correlation, a negative correlation with things like yield and stomatal conductance, GS, and water potential. So you can see that even very simple canopy temperature measurements from 1,000 to 2,000 feet can give us some ideas as far as the variability across an entire region. Another place where this type of technology can be used is to increase irrigation uniformity. I know Jeremy and I have talked about this in the past, but in this case, on the this map of the block on the left side shows 3/4 of the drippers blocked in that bottom right section of the vineyard. And you can see that manifesting in a higher canopy temperature. When those drippers were fixed and the flight was done again with this fixed wing aircraft and a thermal camera, you can see the uniformity of the block increasing. So that's another way of optimizing irrigation, is actually increasing the uniformity across your block, all right? And capturing these irrigation inefficiencies through thermal remote sensing can be a really powerful tool for you. Not something you necessarily have to do every year, but it could be every several years. And finally, we're always trying to relate the vine's physiology with our understanding of how much irrigation needs to go on based on responses of those vines to irrigation applications. So in that sense, it's important for us to understand spatially how do the vines respond. So in this set of images, we've shown you data that are physiological parameters relating to water status. So pre-dawn, for example, is the soil moisture status. Midday is the plant water status at its maximum stress. And the crop coefficient, the Kc, is something that feeds into the evapotranspiration calculations. So here, each of those little nuggets, it may be hard to see, but each of those little nuggets are single vines. And so we can, across several hectares now, using UAV-based remote sensing with the right types of cameras, multispectral cameras and thermal cameras, start to get an indication of the spatial variation in these parameters to inform the placement of proximal sensors, such as those tensiometers or towers or sap flow sensors or what have you. So understanding the spatial variation is really critical to start to optimize irrigation. Same thing can be done by calculating things like stomatal conductance, which is, I would argue, probably the best measure of vine water status there is, because of those nuances between cultivars in response to irrigation availability. Things like photosynthesis are really important in terms of understanding yield potential, for example. So you'd need to also then look into how much photosynthesis is occurring on a vine-by-vine basis. So just to summarize, there was a lot of stuff presented, but I'll just sort of summarize some of the highlights of those things I presented on. Optimization can be done, and this is a great time to start to think about not just irrigating, but irrigating most efficiently using some of these new sensing technologies that are coming online, whether that's a drone or whether that's whether those are sensors that you stick into your vines. And that's something that now can start to inform patterns of irrigation scheduling based on space and time. The spatial aspects come in from the remote sensing, the temporal, high resolution time-based measurements coming from continuous sensors, which we have access to. This next point, I think I can't emphasize how important it is, and Ev has mentioned this as well. All of these things really are determined based on your understanding of how the vine and the cultivar respond to water availability and the atmospheric demand. So having specific thresholds where you turn on the pumps and where you turn off the pumps really depend on how that vine responds to a given level of irrigation. And this is where the understanding of physiology really comes in, and some of these sensors are starting to build that into their models and prescribed thresholds. So again, plant sensing is not new, but the aspects of continuous sensing which make it convenient are actually fairly new. And there are a number of advantages over soil moisture sensing, which hopefully we've shown you today. Some of the things that are now you're going to start seeing more and more of in terms of irrigation technologies in the next 5 to 10 years. Decision support tools that are going to allow you to make decisions for optimized irrigation, not just put on 5 mils of water, but put on 5 mils of water over the next 3 days, 3 mils a day or 1 mil a day or something, based on weather forecasts and predictions of environmental conditions. And bomb forecasts are getting more and more accurate, so we start taking advantage of that. The other aspect that's getting quite interesting with the availability of continuous sensing is the ability to do a hands-off irrigation. We call that autonomous irrigation. So essentially you set your thresholds or you set your target, whether that's yield or quality or a combination of the two. And the irrigation system based on thresholds at different phenological stages will drive the irrigation and keep it within a sweet spot such that you achieve the target that you're intending. This sort of approach will remove the inter-season variability as well, which I think is probably one of the advantages. You're getting a more uniform crop. And I think that's really nice to have, is having that hands-off approach. So you're going to start seeing some of these things becoming available to you in the next few years. That's all I had. And yeah, I think we're taking questions at the end. Any inquiries, please feel free to email. Thanks a lot. Sorry, I went overtime.
Thank you, Vinay. Much appreciated. Now I'd like to introduce Jeremy Giddings. Jeremy is the Irrigation Manager with Agriculture Victoria in Mildura. and has more than 20 years of experience delivering practical and engaging drip irrigation training for grape growers across Australia. After being raised on a citrus property near Wentworth, New South Wales, and attending the University of Adelaide to complete a Bachelor of Agricultural Science, Jeremy has spent more than 20 years as at the Department of Agriculture, in both New South Wales and Viticulture, working on irrigation management across all horticultural crops in the Mallee. Over to you, Jeremy.
Thanks, Robin. Thanks for the opportunity to speak. Can you hear me okay?
Yes, loud and clear.
Okay, thank you. I'll be quick. So Robin's asked me to talk about climate-based scheduling, in particular Irisat, and we'll get to that in a moment. But this is an old image of the research station at Derton where I used to live, and we had an EPAN there where someone had to refill the water every day to measure how much water was going into that pan, which reflected how much was evaporated, and we related that to crop water use. And you had to do that every day, laborious. You had to do it on weekends as well. And then we moved to screens and weather stations where we start measuring ETO. And now we've moved on again, which is what I want to talk about. But what we've always done is we've got this simple equation, and it's to estimate crop water use. And I'll emphasise that it is an estimate. And we've got ETC, estimated crop water use, equals ETO, which we get from a weather station, and Everard touched on this a moment ago, multiplied by a set of crop coefficients, KC values, which are specific, although I think we'll find that they're not that specific for the crop type that you're irrigating. And that calculation can be done on a daily basis to estimate your daily water requirement. And the way we do that, for vines in our part of the world, in the Mallee, at the start of the season, we have a small canopy cover. So we're saying the KC value is around 0.25. At that time of year, the ETO from the weather station is around 5 to 6 millimetres per day. And we multiply the two together, and an average water use figure for vines at the start of the season is around 1 to 2 millimetres. Later on in the season, as the canopy develops, we have a greater water demand. So the KC in this particular case, the crop coefficient value is 0.5. The canopy is increased, there's more leaves, more irrigation demand. We have a higher ETO, it's hotter, it's windier and drier. And you do the same maths at that time of the year. And for this KC value, a typical set of KC values, 4.5 to 5 millimetres of water a day is not uncommon. Weather stations, most regions have a series of weather stations, and this is an example of one in the Mallee, supported by the Water Authority. Each of those blue teardrops represents a weather station, and that is public viewing, and you can have access. You go into those. Other districts have their own. Look up the ETO figures, and they are the ones that are done, that are available in this particular case. The Bureau of Met have their own now as well. This is some figures from the Mildura Airport. So whatever your source of information is, and it might be your own weather station that can generate ETO figures, or something public, then that's what you need, a set of those numbers. And the way we used to use them in a spreadsheet, here we have the ETO. You might have taken that from a weather station. It's 8 mils a day. The crop coefficient for this time of year is 0.5, and we do the maths. And if this case, this is like a check and balance situation. And if in this case, this irrigator is working to a 30 millimetre deficit, you put on 30 millimetres the day before. We've calculated that 4 mils we used today, so we've got 26 left. And you do that every day, so on until you get down to 0, and that triggers an irrigation event. And you start again. And that's fine. And that's the way we can do it. Industry have got their own spreadsheets now, and this is one from the almond industry, which is put in their terms that they're more familiar with phenological stages, etc. They're also more likely with drip irrigation to be irrigating every day and not irrigate to a deficit of, say, 30 mils. So they will do that same calculation every day and work out what the demand was yesterday and replace that the following day or night. So that's the background, and that brings us to Irisat. If you look in the middle of this slide, I've got the calculation, ETC equals ETO multiplied by KC. So it's the same calculation as what we've been using for 30 years. What has changed now is, the internet and all the telemetry that goes with that. So we generate ETO figures from a weather station still, and this piece of software, Irisat, which I'll go through in a moment, finds your local public weather station, or you can use CSIRO, which is that grid of interpolated data available throughout Australia to generate your ETO figure. The main difference, the big difference for Irisat is that we generate the KC value using satellites, and we can generate that KC value specific for your property, specific for your rootstock, canopy size, trellis type, soil type, and patches within your property as well. So that makes it very specific. There's John Hornbuckle, who's behind all this. Some very smart people use satellite imagery and NDVI to turn that into a KC value and do that maths that I just described, do that maths for you. So this is the limitations of the way we've done it in the past. This is, regardless of any deciduous crop type, you start off with a low KC value at the start of the season as budburst occurs and the canopy starts to develop, and then mid-season we have a peak here and then it starts to desiccate afterwards. And in my example earlier, we had 0.25 at the start and 0.5 in December for KC values. What Irisat has helped us enforce is that you get that specific KC value, and all these little blue tabs here represent the KC value at the start of the season. These are all wine grape properties, all in the same region, the MIA, I think, John told me. And you can see the variation that exists. So in the past, we might have been using a standard crop coefficient figure here, the black line, which probably was generated from sultana in Sunraysia on a tea trellis. We don't grow much sultana anymore, and we've got a range of varieties. And you can see here the variation in KC values at the start of the season based on whether they're an early or a late variety and the way they might be irrigated. So there's a huge variation here, and then it starts to tighten up in the peak of the summer around the typical figure. And we see that a lot, that water use in the peak of the season is fairly similar, but there's a massive variation at the start and also at the end. So if we were using this traditional approach in the past, there was a fair limitation. And I think Everard mentioned that it's a bit of a guesstimate what your KC value is based on industry standards. Well, here's an opportunity to start to generate that number for your own property. The way we set Irisat up, it's a Google Earth-based platform. And here I am in the middle of drawing a polygon around a patch at Orimple where we work. You can draw them around individual patches within this block if there's a variety change, etc. But once you've drawn that polygon around and completed it, and you only have to do that once, within a minute or two, the software starts to generate some numbers, some interesting numbers. And the chart on the top here is the KC value for that particular patch. And you can see it starts to rise in September, October, peaking at around about, 0.75, 0.8 as a crop coefficient. And this is probably a reflection of the stronger, healthier, more vigorous vines that we're growing compared to sultana, where we had that standard crop coefficient before. And then you see it start to decline and desiccate later in the season. And the graph at the bottom of the page, the blue dots represent daily water use, estimated daily water use. Doing that calculation that I talked about earlier on a daily basis. And you can see the peak of the season, we're talking about 8 or 9 millimetres a day, almost double what we used to have as under conventional crop coefficient numbers and estimates. The green is cumulative water demand. So this is over the whole of the season. We're talking, 1,000 or 1,100 millimetres here, which is 10 or 11 megalitres. This is some data I got just downloaded yesterday. So the previous data was the full season, the previous season. here we start to see the crop coefficient taking off, and then daily water use really scattered this year given the conditions we've had, as you'd expect. And so unrestricted demand says that we needed about 2 megalitres so far, 200 millimetres on the right-hand side there. The beauty about Irisat is it has some scheduling potential. If you put in anti-irrigation events, once you've set your polygons up, you can start to get an irrigation trace, and you put in your readily available water figures and determines your refill line. You can start to have some irrigation scheduling opportunity here on the left-hand side. On the right-hand side here, the green line represents estimated crop water use, and each of those irrigation events or rainfall events is represented by a step here, and you can see how close you are to maintaining unrestricted growth based on estimated crop water. The other beauty about Irisat, and a couple of the presenters mentioned this earlier, is we're looking in the future now, and this is downloaded this morning on the patch of vines that I showed you earlier, and this is estimated ETO for the next 7 days, so you can start to make some planning decisions about that. So we've got a very low ETO expected today, and it starts to dry out and warm up tomorrow and get up there, and Thursday next week quite warm again. The graph down the bottom is just a chart representing the same thing, and it's saying that if we look at the cumulative again, the green, over the next 7 days, we're looking at about 5.5 millimetres of water requirement that's going to be needed. The thing I like about Irisat, and probably the thing that is most attractive at the moment, is we think it's an introductory level opportunity to what Vinay talked about earlier, that precision ag. You get what you pay for, and you don't have the small, 50, 20 centimetre pixels here. These are 10 metre pixels, and you can pick up the crop variation across your vineyard. And in this particular case, this is one due to a poor drip irrigation system where the emitters weren't performing the way they should in the top left-hand corner. So it gives us some opportunity there to start to pick up why that's happening. In this case, it was an irrigation system problem, but it could be soil, it could be disease, it could be anything. But I think it's an introductory option. Irisat is a free piece of software available to everyone throughout Australia on a range of any crop type, as long as you've got green vegetation. It doesn't work for red lettuce. It doesn't work if you put plastic over the top of your vines. But for any sort of green vegetation, it's fairly handy and a good introductory option to do that. And our department provide, with Maxine, Shaki, provide workshops on this sort of thing to set you up on your own computer at home and draw these polygons and start playing around and start understanding some of the numbers. That's it in a nutshell. Robin also asked me just very quickly to cover some aspects to consider when selecting a sensor, and then there's an enormous range, and you've heard some of those this morning, enormous range that are available. I've been doing this type of presentation for 20 years and it hasn't really changed. I still think there's three main things to start thinking about if you're going to select a sensor or a tool, whether it's the one I just mentioned or any of the others from the previous speakers. The first one is the after-sales service, the support and the agronomy. And this is really important. It's all about having someone who is able to get the tool to work for you. And we know they all work in the laboratory, or they all work for researchers, but do they work for the practical irrigator out there? We used to say that this means having an agronomist in your region. I think that's a bit looser now. You can do a lot of things on the computer. Your agronomist can be in New Zealand or wherever, as long as he gets access to your data and has a look at your trace or your data and can make some comments and give you some feedback that way. But certainly the backup and support in a general sense is so important. Seen recently, irrigators install multiple sensors of things that really had no support, and it is a shame. The second point is the data presentation, having it in a form that is easy to understand and use. And remember, at the end of the day, all we want to know is how much and how often. And this is a typical capacitance probe that was touched on by Vinay. And here, you know, the refill line here, we know an irrigation needs to go on here. This is when you should have irrigated, a day before you did. And any readings in the blue up here are too much. And you get an understanding of how many hours you need to apply there. I mentioned earlier, we're starting to get away from irrigating to a deficit. We're starting to irrigate every day. And as a result of that, we're starting to get away from the summed graph, which is this one in green, and start to look at split level graph and just see that we're maintaining our soil moisture levels at an acceptable point. And you can see here a bit after December 9, or maybe a bit before, we're starting to not maintain our soil moisture at 70 centimetres and may needed to add half an hour to an hour to each irrigation event from then on in that particular case. We've also got data and presentation modes like this, which are just way off and very hard to interpret, and blow you away with complexity. The thing we're starting to see more and more is integration, and this is a similar irrigation trace at the top here, but at the bottom we have integrated rainfall events from a weather station. You don't have to enter these manually anymore. And you also got a little sensor out in the field measuring drip line pressure. So that is a substitute for irrigation events, and you can see each of these blue ones are an irrigation event and a corresponding rise in the irrigation trace. And in the middle of May here, that valve got stuck on, and you can see the end result. The other thing that's starting to get more and more interest is there's companies around now that integrate all readings. So integrate, and you heard Everard talk earlier about how plant-based sensors and soil-based sensors are a good combination. The problem in the past is they've been on two different pieces of software. There's companies around now that can start to integrate that software and make irrigation decisions much more easier by having that sort of data. And this is not a great one to show, but there's others around that not only integrate what you might be doing for irrigation, but also some of your hardware as well. So data presentation is important. It needs to be put in a format that makes it easy to interpret and understand for you. And the final one is to think about whether these tools are being used in practice out in the field, in case studies, examples in history. And I've mentioned an example a moment ago where an irrigator has installed 20 sensors, no previous history of that crop type or in that region, and it's made life pretty hard for himself. So you need those examples of reality, real examples in the real life world about how they're being used and used well. And that's all from me, Robin.
Thank you, Jeremy. Now I'd like to invite Vinay and Ev to rejoin us for the Q&A session. So Vinay, a question for you to get things starting. You talked about the sap flow sensors requiring calibration. What about the thermographic sensors? I imagine there's that calibration component to that too. Yeah.
Every type of sensor we use requires a calibration, whether we do it or whether it's done at the factory. But I would suggest it's done at this point of installation.
Great.
So, yeah, they would all need calibration. That's right.
And I think you touched on that also, Jeremy, with the free program. You still need to go out there and have a look on the ground to make sure that the variation that you're seeing in those graphs are actually related to irrigation, or whether it's soil, or whether it's pest and disease, or what it is that's creating that variability. You can't just make an assumption.
Yeah, absolutely. And hopefully photographs like I showed you trigger you to get out there because there's something going on. Yeah.
Great, thank you. So we've got a question. Is there any suggestions for using ETO for subsurface irrigation scheduling?
Yeah, absolutely. I guess in the past, you would have question marks about what your KC value would be, because you've knocked out your surface soil evaporation to a large extent. A tool like Irisat, you can generate your ETO, your KC values, your crop coefficient values quite easily and quickly under any scenario, whether it's subsurface or sprinkler or whatever.
Just on that KC value, it was really interesting, the graph that you showed that showed the huge variability at the start of the season, depending on the variety, the irrigation strategy, the soil type, I imagine, but also things like, does that take into consideration things like the amount of weed growth or the cover crop that you have, things like that?
Yeah, and that's a strength and a weakness. All it's measuring is green vegetation, whether it's weeds or your canopy. And we've got an irrigator who, in our case studies, talks about how a patch of vines had a higher demand than he thought, and it was due to weed growth. And the software doesn't differentiate that. Some of the more sophisticated ones can, and can remove mid-row reflectance, but the Irisat's quite a crude and introductory level one that just measures green vegetation.
Yeah, but I guess for growers who are just starting out with this sort of technology, the fact that it's free, it's available online, you can get your training through AgVic, it is, an approachable way to start off in this area. And Vinay, your comment about with the soil moisture monitoring and plant sensors, taking into consideration the variability in the vineyard to know where to put these different sensors is really key as well. Just with the thermal sensors, Vinay, is there a particular time of the day that you need to do those flights to make sure you're getting an accurate measure of that, the differences?
I mean, yeah, so if we just, think back to what Ev was talking about, in the concept of thermal sensing, you're actually trying to estimate the transpiration rate. It's not the transpiration rate, but it relates very strongly to the transpiration rate. So the higher the transpiration, the cooler the vines. So you're really trying to find a time of the day where the transpiration rates are at their highest, right? Their potential values. Now, obviously, they could be low because of soil moisture stress or high VPDs and things like that. So, for us, sort of, and it depends on whether the day is a heat wave day or not. So the stomata will start to shut down earlier in the day if it's a hot day, if it's a 45-degree day. So the maximum transpiration rates then occur sort of in the mid to late morning. But on a typical day, I would say it's, solar noon. So like 12, 1, 2 o'clock around that time.
Okay.
I don't know if Ev has more, you have a lot of experience too about the timing of this measurement. Yeah.
No, look, I would agree. I mean, and obviously you want good sunlight on the vines as well is the other thing, but yeah.
I think that's one of the drawbacks of using these temperature-based measurements is if you have cloudy conditions or it's wet, that temperature measurement is no longer reflecting the true water status of the vine then. So that's the limitation, I think, of that measurement.
Okay, great,
Yeah.
thank you. We've got a question about whether these thermographic or the thermal sensors can be used as a substitute for the soil sensors, soil moisture sensors, or do they go hand in hand, really?
I think it's nice to have both because, as Ev was saying, you have these soil tension sensors. They don't tell you mils of water in the soil, so you don't really know how much to put on. And it's the same thing with the plant-based sensors. You can't really figure out how much volume has to go on back into the soil through irrigation. So I think having a combination of sensors is the best situation if you can afford it, because A, you know how much is in the soil, and B, you know how stressed the vines are or how much water they have access to, given what's in the soil around the sensor. So if you can afford both, I would say do both. If you can afford only one, do the plant sensor. That's just my inclination. Yeah.
Okay. So the soil moisture sensors, are they really to help you work out when to start irrigating at the start of the season, or even over winter if you are getting dry winters and you're getting a deficit during winter? Does it tell you when you need to really start applying the irrigation? And then I think in your graph, Jeremy, you had a really good example of working out how much water to apply so that you're not losing any through the profile, or not drying out the lower part of the profile. So I guess particularly if you're starting out with a new vineyard, having that having soil moisture sensors will help you really understand how your soil responds to irrigation, and the plant sensors will really help you to fine-tune that information. Is that how you see it working, Everard, Vinay, Jeremy, all of the above?
I guess, yeah, I mean, obviously these things all link in and they're all giving you slightly different information which you can combine, or ideally whatever management system you're using will combine them for you. So if you've got really good ETO estimates, whether it's ETC estimates rather, whether it's from Irisat or whether it's from another commercial company, you know, any sensor you use can effectively be a check on what you're doing. You're using it to monitor how good your measurements are. So from that point of view, you could use just a soil sensor or just a plant sensor or so on. But, you know, you do risk obviously missing some signals. So I think there's a real range, and I think increasingly we'll see commercial companies that, you know, as Jeremy showed, that pull that together for you and, you know, give you the warning flags and do a lot of the hard work.
Okay, now I had a few extra questions that I've written down. Where are we? No, can't find them. Is there anything anyone else would like to add? So for more information on these types of sensors that are available, do you recommend jumping onto the Uni of Adelaide website or CSIRO website? How do people find out more information about this?
We don't really have much on the website, unfortunately. I think you probably DPI. I thought, Victoria, Jeremy, do you have a portal where you have plant-based sensors and soil moisture sensors listed? I thought I saw something at some point.
Yeah, we do actually, as an introductory. And starting to differentiate between what different ones mean, because we have seen that we've almost overloaded with information, and we're trying to simplify that. So yeah, I think most departments will have some sort of fact sheet on as an introductory level on any of those tools, you'd hope, and then maybe you progress further with the commercial option.
Okay. Now I did remember my question, Vinay, this one's for you. There was, you showed a graph where it was a Shiraz and Cabernet comparison, and you showed that the Shiraz in particular had a much higher water use efficiency when you used the plant sensors to schedule the irrigation compared to the Cabernet. Can you talk about why there was a much bigger change in the Shiraz compared to the Cabernet?
I think the simple answer to that is the Shiraz was getting a lot more water than the Cabernet. So by cutting back that, we could cut back more water without seeing a negative effect on yield and quality in Shiraz, because it was just getting more water. And you may not remember, but the soil moisture levels of those Shiraz vines were quite a bit higher.
Okay.
And they were getting more moisture throughout the season, and they were bigger vines as well. So just because of that, there was more opportunity to save more water, I guess. It's very simple, yeah.
Okay. You did talk about that varietal difference, though, didn't you? And you said that the Cabernet, I believe, shut its stomata earlier than the Shiraz in response to water stress. So
that's right. That's right. And what we saw then is because that stomatal closure was occurring, it was a bit more sensitive than Shiraz, at least based on the data that we have. And there's a debate around whether Cabernet is, more sensitive or less sensitive. But in this case, we saw that it was a bit more sensitive than Shiraz. So it tended to shut its stomata in response to a soil drying. And as a result, the water potential starts to rise. And that's where I then concluded that, well, it's incorrectly telling us that the plant is not stressed when it actually is.
Yep. Okay.
We know the soil's drying up, so there's less water.
Yep. Yeah. Okay. So we have a question. You're all referring to using various companies. If you're starting a new vineyard, what companies do you recommend contacting? So maybe jump on the AgVic website and have a look at the info that they've got there, and then you can work out where to go. Jeremy,
I don't know why Australia has anything on their website with different types of vineyard technologies and things like that. Do you know? Why Australia might have something on their website?
They do have some information. Yeah, I feel like there might be a bit of a gap here that we need to fill. Jeremy, your thoughts?
Yeah, I think it's a bigger question than this, but whatever company satisfies those three basic points that I mentioned at the end there. But talk to the neighbours. You'll find that a certain tool is more popular in a certain region than others, and you can't be too generic, and it's probably based on the level of support that exists in that region. And that's probably a good start. Yeah.
I mean, one other aspect is going to be the margin in your crop. So if you need a tool that's, giving you good information on 600 hectares in the, Murray Valley or Riverina or Riverland, that's going to be quite different probably from a tool that's giving you good information on 20 hectares in upland Tasmania. So, the detail and how much you can afford per hectare is going to vary a lot.
Okay, wonderful. All right, thank you very much for our presenters for the really great presentations. Lots of information you jam-packed into there. And thank you also to the audience for your questions. Just a reminder that this webinar has been recorded, and the webinar recording will be emailed out to you. We have another webinar coming up next week, next Thursday, on reviewing the standard procedures for grape sugar and colour measurement. So if you're interested in that webinar, jump online and register. Look forward to seeing you again. Thank you, everyone.
Thank you.